Grazie Giovanni, grazie mille anzitutto per l'invito a moderare questa sessione. Hai già presentato anche i colleghi che con me modereranno e cercheranno di tirare le fila di questa prima track. Sono 5 lavori che verranno presentati, lo dico per gli speaker, tutti in sequenza, uno dietro l'altro, senza la pausa prevista per le domande. Questo perché per rendere fattibile anche la comunicazione delle domande eventualmente da chi fosse nell'altra sala ed evitare quindi i ritardi, le domande verranno poste tutte alla fine. Quindi chiedo a tutti gli speaker che interverranno di venire al termine della presentazione, lasciare il podio per lo speaker successivo. Alla fine di tutta la sessione vi richiameremo in maniera tale che possiate rispondere alle domande che saranno nel frattempo pervenute. Non ritengo di dover dire altro a livello introduttivo, vi segnaleremo, ecco, l'unica cosa, se ci stiamo allungando un po' coi tempi, vi segnaleremo quando manca un minuto alla fine della vostra presentazione. Quindi direi di non perdere altro tempo e invitare subito il primo speaker, che è Alessio Luschi dell'Università di Firenze.
So I'm switching to English, and my name is Alessio Luschi. I am working at the Department of Information Engineering in Florence, and also the Department of Medical Biotechnology in Siena. And I am here lecturing about applying natural language processing techniques to extract real-world evidence to for health technology management, health technology assessment, and for post-market surveillance as outlined in the medical device regulation, in the European medical device regulation. And I'm the first one, so there's something. Okay. Switch. To extract real-world evidence, we need real-world data. They are data that are extracted from real-world practice in the field, and there are several sources they can be extracted from. There are surveys, there are electronic records, there are social media data, and also spontaneous reporting systems. These are databases where adverse event reports are stored according to the medical device they are referring on. And the most famous are the mode of the VIRES and the FHIRs of the FDA, they are American of FDA. We also have the EUDAMED data bank of medical device, which we will be able soon to extract data from, but so far is still closed and not publicly accessible. And we decided to narrow our study only on health information technology. So we only took in consideration the technology that are based on information of medical devices and not the whole classes that can be available from extracting these reports from the database. To make a computer understand what is written inside a human written report, you need to apply some techniques where you can teach the computer how to manage this information. Natural language processing is a subfield of artificial intelligence that aim to do so. So we can teach a computer to understand semantic meanings from a human written text. Mainly, natural language processing is divided into branches. There are natural language generation and natural language understanding. Natural language generation, you all know, ChatGPT is that one. So you can teach a computer to produce some text that there can be mistaken for as written as from by human. For our purposes, we need to natural language understanding. We need to understand what is written inside these adverse event reports. And the gold standard so far is the BERT models developed by Google, where BERT stands for bidirectional encoders representation for transformers, is the architecture behind that. Okay. There are several BERT models available, depending on which text they are trained. There are Roberta, DistilBERT, ShyBERT, BioBERT. In this case, we use clinical BERT, which is a BERT model which is trained on clinical nodes. So for our scopes, is the one that we thought was the best fitting, the best suited option. So this is the proposed solution. We extract adverse events reports from the MODE database. It's about 3,000 records extracted in several years, and we labeled that in two classes, mainly two classes, HIT and non-HIT, where HIT stands for Health Information Technologies. That we apply our BERT-based models, so our clinical BERT-based models, and fine-tune it on these 3,000 records. And we extract real-world evidence that can be further classified to according to the faults that are reported inside the text. We can have some operation system faults, lack of training, network issues, or other kind of faults. And the outcomes of the whole model can be used to, as I mentioned before, for evidence-based maintenance, health technology assessment, and management. So in the first step, we analyze the extracted data. We find that the majority of the text was less than 512 words in length. So we decided to truncate all the text at 512 tokens, 512 words. This can help the models in training. This can ease the training process. And so we, as you can see from the slide, we only use 4 epochs of training, which were enough to train the model, to fine-tune the model on these records. We then apply a tenfold validation on the whole model, and this is the results. You can see that the fold number 10 is the best performing one. And we test that fold on 20% of the whole data set, which was about 700 records. And the results are shown in the bottom part of the slide. You can see the ROC curve and the confusion matrix. And we can see that the model just mistake 7 records on the whole testing data set, 6 false positives and 1 false negative. We also compare our model, the results of our model, to other existing models that were about the same topic, but that didn't use BERT-based models. And we find that our model is the best performing one in terms of accuracy, precision, and recall. The other models used linear regression, support vector machine, convolutional neural network, but they didn't use BERT-based models. We also apply some explainable AI tools to the process, to the data set, to understand which were the reasons that were behind the decision of the model in terms of classify one reports as hit-related or non-hit-related. We mainly use two tools. They are the gold standard tools for explainable AI, which are LIME and SHAP. This is LIME applied just to one record of the testing data set, and we can see that words like images and system are the main responsible for bias the model toward the hit class. Okay, so we can see that these are the token, the words that the highest weight. Then this is the SHAP values applied to the whole data set. So these are the main keywords, the main word that were representative for each class. in the whole testing data set, and we can see that word like handheld, computer, software, programming, packs, images, have all a positive weight in terms of the hit class. This is understandable, even from when we see the outcomes, the outputs of the SHAP values, we can see that it's coherent that words like computer, software, programming have an highest value, highest weight for the hit class. And we can also see that the first word, handheld, has the highest weight in the whole data set. This is because the majority of the extracted reports, of the extracted 3,000 reports at the beginning, were about faults of handheld devices. So this is an evidence that can be easily extracted from this kind of tools and this kind of explainable AI application. So in conclusion, we design and we develop these natural language processing BERT-based models that can automatically identify adverse events reports and classify them in health information technologies related and non-related classes. We find our results show better metrics than other existing NLP models that are not based on BERT. And the next step of this research, we consider the identification of faults within identified reports. And as you will see in the previous slide. And after that, we can also use the outcome in a more specific way to use the evidence for the purposes that I mentioned at the beginning of the presentation. So that's all. I think I stand in the 10 minutes mark. Okay.
Absolutely. Thank you.
Perfect. Thank you. So now it's time to welcome on the stage the next speaker, Enrico Longato. He's going to present dynamic Bayesian networks and transfer learning enable the development of deep sequence-based models on small sample data. Thanks.
Okay. Thank you for the introduction. I'm Enrico Longato from the University of Padua, and my talk today is about how we can combine dynamic Bayesian networks and transfer learning to learn good predictive models even if we have only few data points. This should be, if the slides will be, all right. Okay, so this is a frequent enough scenario, as I was trying to say, especially in the field of rare diseases, because as you might imagine, assuming this goes in the right direction, which it doesn't, no? There you go, fantastic. All right, as I was saying, challenges in the field of rare diseases all come from the fact that these diseases are rare. And this means that there is an upper bound to how many data points we can have because there is a limited number of people who have the disease, which is a bit of a problem if we want to use high-capacity models, that is, models with a lot of parameters that have been proven successful in other fields but are difficult to use here. Okay, first objection, you might say, well, just do some data augmentation, which would be nice, except these are not images, so we can't rotate, translate them, and do stuff like that, because it's unclear what it means to rotate or translate a patient. Lots of problems, but nevertheless, we want to train a complex model, and in this case, a deep learning model that can ingest sequences and make a prediction. So what do we do? Well, we'll see that on a case study, which is about amyotrophic lateral sclerosis, which is a rare disease, fortunately enough, because even though it affects only 1 in about 10,000 people, it is always lethal, so it's great that it is rare. A modeling task will be quite a standard one, that is, we will try and predict death within 3 years, and do that using the longitudinal data from routine visits. Our strategy will be as follows. First, we will take a small sample database and try and build a model with that. Then, realizing that maybe it's not the best of ideas, we will build a simulator to augment our data, and we will do that with dynamic Bayesian networks. At that point, we will train a model with the simulated data, and eventually we will try and mix and match the simulated and real data to converge on the best possible performance using transfer learning. So let's go on with that. But first, here is our data set, as I was saying before. Rare diseases, very few people, very few data points. This is a registry of ALS that covers basically 2 regions of Italy. And as you can see there, it has about 600 patients, so not much, even though it's a big area. What you find inside is what you generally expect. So you've got demographics, clinical measurements, etc. And the interesting thing is that a few of these variables are dynamic. And those are the ones that we want to incorporate into our model. So first things first, we've got a small database and we want to augment it. We do that with dynamic Bayesian networks. So dynamic Bayesian networks are probabilistic graphical models that encode the conditional probability dependencies over time among a set of variables. So basically what you get is a graph like that, where you've got the evolution and the interrelationships between variables and the way that they work over time. You train a DBN using longitudinal data, and once you've trained it, well, you use it to simulate the evolution of population starting from some initial conditions, for instance, the ones from your original data set. Now, the good thing about these models is that they are explainable, because you can always check if what has come out of your training makes any sort of sense. And in this case, it does. Unclear if the picture is clear enough, but I've highlighted a few literature relationships. So our network works because it can see that age at onset and onset site are correlated, which is great. That's what the literature tells us. Same thing with sex and diagnostic delay, because we know, unfortunately, that women's symptoms tend to be underestimated, whereas men do not go to the doctor, so that's good that we have that relationship there. And then we also have a few common sense relationships. So if the patient has trouble breathing, maybe they will need ventilation. And if they have trouble swallowing, maybe they will need a gastrostomy. So we are quite confident that our Bayesian networks actually works. And since it does, we take our little data set and augment it 100-fold. And we get a bigger version of it. It will always be read in the following. And that's our simulated data set with about 60,000 patients. So here are the databases. Now we need to combine them. And we do that using transfer learning. So transfer learning is a bunch of techniques that are used to transfer knowledge between tasks. So we have a task that we know we can solve. That is, we have simulated data, lots of data, and we want to build a model. So that's easy enough. And a target task that we are not sure that we can solve, but that we need to solve anyway. That is, we build a model on the small data set of the real data. And to do that, there are many alternatives. We use one that is called fine-tuning, and it works like this. We train a model only using the simulated data. We call that model the encoder, but that's just a parlance of transfer learning. Then we remove the output neuron and substitute it with a subnetwork that we will then train in a very specific way. So first, we take the real data, so no more simulated data, and let only the new bit that we've added change its parameters, fixing the encoder. And only when we're satisfied with that, we let the model finish training, and in doing so, we have a model that started from the simulated data, but now works on the real data as it should. Okay, so these are the techniques, and the entire pipeline looks something like that. We simulate 100 times our patients with DBN, then the data look like that, the variable length sequences, and we turn them into vectors via a recurrent layer. At that point, we can use that as normal, so we've got a fully connected bit. I've already removed the output neuron, so that's only the final bit of the encoder, and then we do fine-tuning on the real data. Let me show you that. We have both the blue and the red boxes, meaning that we've used both the simulated and real data to get to our goal. So we do that. There's a bunch of other stuff that I will not show because it's too complex for the few minutes I have. But so let's go to the main result. So we've done all that complicated thing over there. How does it compare to what you would normally do? That is, you just do the model and you train it with only the real data. Just to be clear, the bits that are missing, as you see, are the DBN and the simulated data, and the final bit of the network that we used for fine-tuning. So what happens in the normal case, only real data, is as expected as it is disappointing. Because, obviously, if you have 500 sequences, almost impossible to get a working model of that complexity. Now, if we simulate the data, then apply transfer learning, things are not earth-shatteringly better, but they are better. And they show that we can get a 10%, more or less, a gain in performance using the same data, except augmenting it in a clever way and using fine-tuning at the end. So we get all the information that we could squeeze out of the data set just by doing a little more calculations. And this is quite interesting, and we will see it in a second at the end of the conclusion, because it shows that if we combine dynamic Bayesian networks and transfer learning, we can build effective models even if we have almost no data. And this is important because in the example that we showed, that is one of the rare diseases, ALS, we've seen that a small sample data set doesn't really work. And the moment we add a DBN plus transfer learning bit, what we are doing is basically we are making an entire class of models viable again, because before it was a fool's errand to try and train all those models with those parameters, but now you can. Maybe it doesn't work super well, but at least it's doing something that you can compare with other models that you might want to try. And the interesting thing here is the following. So first, DBNs are explainable, so we've solved the problem of how do we translate and rotate patients, because we just simulate them in an explainable way. And finally, even though the pipeline I've shown was super complex because you have the simulations and the fine-tuning, etc., if you build a model, all the complexity is on you. The moment you ship it, you give it to someone else to use it, they will see a normal model, a normal deep learning model. They can just plug and play and get their own prediction. And so that was it from me. Thank you all for the attention.
Good morning, everyone. Thanks for the introduction. And my name is Giulia Sedda. I am from the University of Cagliari. And today I want to present you iLab, a user-friendly MATLAB tool for real-time monitoring of eye movements. As we know from the literature, eye movements are very, very important to predict, document, and diagnose multiple neurological deficits. For example, if you have prolonged latencies in simple saccades, this is very common in advanced cognitive impairments, such as in dementia. Or hypometric saccades are typical in Parkinson's disease, reflecting also the hypokinesia seen in limb and hand movements. Another example, reduction in pursuit gain is reported in patients with schizophrenia and with mild traumatic brain injuries, and so on. Usually, these abnormalities in binocular movements are large enough to produce disturbance in patients, but at the same time, they are also too small to be highlighted by subjective evaluation. So we need quantitative analysis of eye movements to obtain oculomotor measurements, quantitative measurements, with very high spatial and temporal resolution, to permanently record and store this data, and also to process them, post-process them, and analyze them. Unfortunately, clinicians used to, in the current clinical practice, used to prefer the subjective evaluation and often refuse the use of advanced eye tracking technologies Why? Because they are very expensive, very difficult to use, as they require non-negligible programming skills to the user, and also are usually closed system. So you have a standalone device with proprietary software, and the clinician has to learn how to use it. For this reason, you need iLab. iLab is a novel open source tool with very intuitive, user-friendly graphical interface, many features, for extending the capabilities of a specific eye tracking. They are linked to eye tracking system by SR Research that you can see in this video, without requiring any programming skill by the user. This is intended for both clinicians and researchers, with the aim to adopt this advanced technology in the clinical practice and also in research for the best clinical and research advantage. This tool allows the user to visualize in real time the data and also sample it, store and analyze. The iLink 2 system is very complex and sophisticated. It is composed of a host computer which hosts the system application and is connected to the headband, which embeds 3 cameras, 2 for binocular tracking and 1 for the head tracking. It's also connected to the 4 infrared active markers, which are placed on the corners of the patient monitors, where visual stimuli are displayed by the displayed computer connected to the host computer. The host computer is also connected to the iLink 2 monitor, which is intended for the clinician. Here you have the proprietary software and a very old-fashioned and low-intuitive interface is used by the clinician or by the user in general to set up the cameras and also set up the procedures such as the calibration, validation, and so on. iLab adds something new, add a 3rd monitor intended for the clinician, providing a real-time control interface, which is very useful to customize the experimental procedure, to manage data acquisition in real time, data visualization, processing, and storage. iLab is composed of 3 main windows. The main one is the real-time analysis interface, from which you can move to the other windows. In particular, from this interface, you can select the sampling frequency of the system and also other features of the monitor, as you can see from the video. Then you can customize the graphics by which you can monitor in real time the data, and then select one of the proposed already implemented experiments with their features. Okay. Then you can move with the start button to the experiment, and then the clinician is allowed to monitor the binocular graph of both position and velocity, which are updated in real time during the experiment. From the real-time interface, you can move to the offline analysis interface to post-process the data in order to detect smooth pursuit movements, saccades, blink, fixations, and so on. So from the real-time interface, you can first of all look at the data, so see the time series of the binocular movements. And for example, if you want to perform a saccadic analysis, another window is open, and here you can select the eye, the kind of analysis, the algorithm that you want to apply to the data, and other features. And then each saccade is plotted 1 by 1, so you can select which saccade you want to analyze. You can also select all of them. And then they are reported in this list, where you can also add some correctives, so modify this selection, and then generate the related analysis, which is shown here. There are many possibilities. For example, You can see the left and right eye position and velocity, or you can also analyze, for example, the duration, the latency, the gain, and so on. Finally, the protocol-based interface. This is the most interesting, probably, because the clinician can create a new protocol and customize it with a very, very intuitive way. So first of all, you select it from the real-time interface, then you move to the protocol-based window. And here you can load a previously designed protocol, or you can create a new one. You can select, for example, the target shift interval, its distribution, or if you want to randomize degrees and directions. You can select the number of saccades, so the target that you want to use. You can also choose the movement direction of the target, horizontal, vertical. And then when you finish the selection, all the targets with their degrees, direction, and time, are reported. And if the clinician is happy about that, is satisfied, can save this protocol before he has to select a name, and then save the protocol file to use it immediately or later. Okay, so to conclude, iLab is an open source, user-friendly graphical interface which integrates intuitive features to extend the conventional capabilities of the iLink 2 eye tracking system without requiring any programming skill by the user, and allowing the clinician, first of all, to monitor patient binocular signals in real time, such as, for example, saccades, smooth pursuit, fixations, and so on. In addition, data can be recorded, stored, and offline post-processed. Moreover, iLab can be installed on different operating systems, such as Windows, Linux, macOS, and has been developed and currently being validated with clinicians with the aim to introduce and adopt widely this kind of advanced technology in the clinical practice. At the moment, iLab can extend functionalities on iLink 2 system only, but other extensions can be easily implemented. Moreover, the application was developed under a MATLAB academic license, and as the application is standalone, it can currently be released only for educational purposes, but this point can be updated. The great news is that the iLab source code will be released for free in the next month, so if you are interested in it, please stay tuned to our website, the MediaSP website, for more information. Thanks a lot.
Multi-input, multi-output model predictive control for drugs delivery in clinical anesthesia. So welcome, Eleonora. Okay. The floor is yours.
Thank you for the nice introduction. Good morning, everyone. So, thank you. So, in clinical practice, the control of anesthesia is done manually by the anesthesiologist. And the anesthesiologist asked the bioengineering community if there was a way in our set of skills that we could help them managing anesthesia. And the solution was found in closing the control loop of anesthesia and somehow helping the anesthesiologist performing their tasks. So what does it mean, and what are the advantages of automating delivery of drugs during anesthesia? So the advantages are many. First of all, we have a faster sedation Then we have an increase in safety that is due to the fact that we keep monitoring all the vitals and the drug infusion profiles, and we have under control in a continuous way what are the important signals in anesthesia. Then we have a reduction of the total amount of drugs that are administered that can lead to a faster postoperative recovery and overall fewer side effects. This is from the patient perspective, but what about the anesthesiologist's point of view? So with this automatic control, we can benefit the anesthesiologists too, since we are able to reduce some of their tasks, making sure that we reduce their workload and we can avoid, for example, fatigue and weariness, typical of this role. So some key aspects of clinical anesthesia. So it's made up of 3 different stages. The first one is the induction, in which the patient is brought from consciousness to a certain level of anesthesia. And this is done by infusing some drugs. Then we have the maintenance phase, in which the patient is kept in that level of anesthesia and the surgery is performed. Third, we have the emergence, in which the drugs are stopped and the patient is brought back to consciousness. We have 3 different components of the anesthesia itself. The first one is the neuromuscular blockade that is related to the absence of spasm during the surgery. Second, we have the hypnosis that is related to the loss of consciousness. And third, we have the analgesia, that is the suppression of the pain feeling of the subject during the surgery. This can be achieved using 3 different categories of drugs. The first one is a neuromuscular blocker. The most used one is atracurium. The second, we need something to control the hypnotic state, and this is propofol. And then thirdly, the most common analgesic in clinical practice is remifentanil, so we will use those. We said that we want to control somehow the level of anesthesia, but what does that mean? So we can quantitatively control anesthesia using some indices related to the 3 main components. For example, we have a monitor that says from 0 to 100 what is the neuromuscular blockage of the subject during the surgery. We have the BIS scale for the hypnosis, and then we have the RAS score for the analgesia. So how can we develop our control strategy and how can we test it? So to do that, we used a modified, updated version that we updated ourselves of an open source anesthesia patient simulator that has been developed in MATLAB Simulink and by Ionesco et al., available since 2021. That is basically a model that captures the relationship between the infusion of the drugs of anesthesia, the one that we saw before, and the drug effect on the subject's body. So the inputs of this kind of simulator are the anesthesia drugs that are, as we saw before, the propofol, remifentanil, and atracurium. And output, we have the monitoring indices of anesthesia. In this kind of scenario, the surgery itself is seen as a disturbance, since it acts on the depth of hypnosis and tries to awake the subject somehow. We have at our disposal 24 virtual subjects, and we have, in our modifications, made some realistic changes so that, for example, the surgery is personalized in a random way on every subject, so in its length and its intensity. And we have added even some measurement noise on the 3 indices of the output indices. So what is our objective and our proposed approach? So we developed a model predictive control, the so-called MPC, to be able to regulate the indices of anesthesia and the depth of anesthesia by automatically infusing some anesthesia drugs and control the infusion rate. As we said before, the novelty of this kind of approach is that this time, using MPC, we are able to consider at the same time a multi-input, multi-output approach. And this is unseen or rarely seen in the literature. How does MPC work? Just an easy sketch here. So let's focus just on the depth of hypnosis, using the BIS monitor as a reference and using the propofol infusion as the anesthesia drug. At each control instant, for example, here we are in K, the MPC will look for the optimal, the best sequence of control action, and in a finite prediction horizon. Here, for example, it's right 3, and the best one is the red one. Then it will apply only the first action in this sequence, following the so-called receding horizon principle. After that, it just repeats, so it looks for the optimal sequence again with updated measurements, and will find and apply just the first control action. So we said that we choose the best sequence, so how do we do that? It's solving optimization problem, and the optimization problem means that each control instant we will minimize a quadratic cost function that looks like the following here. So it's made up of two terms. The first one will penalize the differences between the future behavior of the process that are our anesthesia monitors, and with the reference set point that's known by the literature. The second part on the right penalizes in a similar way the differences between the future drugs, infusion rates, and the basal value. So with the target range in the monitoring indices is known by the literature and is reported here. What we need to find out is how to evaluate the performance of our controller. So to do that, we consider 3 different metrics. The first one is the time to target. That is the time required to reach the target range for the first time, as we see the red arrow. The second one is the nadir of the BIS, that is the lowest value of the BIS observed during the induction phase. As we said before, it's the first part of anesthesia in which the subject is brought from consciousness to a certain level of anesthesia. And thirdly is the timing range. That is the percentage of time that of the indices spent in targets during the maintenance phase. That, if you remember, is the phase in which the surgery is done, is applied. Those are the results of our control algorithm. As we can see, for the time to target for all the indices, we stay in less than 4 minutes. That is the requirement of the literature. The nadir of the BIS is a median value of 47. That is inside the safe interval for BIS. And then the timing range is quite high. Of course, the requirement is as high as possible. And we arrived at, for all 3 the indices, to a high value. Those are the results, just presented in a graphical way. We have on the top row what are the drugs of anesthesia, and on the bottom row we have the indices. So as we can see, for all the 3 indices, we are able to induct anesthesia quite quickly, and during the maintenance phase, we stay in between the safe clinical range. On the BIS graphic here, we can see that on top we have a red line that is the mean disturbance, that is the mean surgery profile. And as we can see, we have a good disturbance rejection. So this brings me to the conclusion of my presentation. We have seen how can be important to automate the drug delivery in clinical anesthesia for both the patients and the anesthesiologists. We have used a modified version of an open source patient simulator to try to design and test our control solution, our model predictive control, and that gave us some ideas for the future developments that, for example, can be the addition of other signals to make our simulation even more realistic and complete, for example, taking into consideration even the hemodynamics of the patients. With that said, I finished. I thank you for the attention.
Thank you. Thank you very much. And very happy to be here today. I'm going to talk to you about this topic today. I'm actually presenting on behalf of Pier Giuseppe Liuzzi, that is doing his research period abroad. And the topic is, can we say something more about consciousness disorders by taking a look at heart rate variability, for example? What is a disorder of consciousness? Well, we are talking about very severe patients, typically with a severe acquired brain injury, that stay in coma for more than 24 hours, and then they move to the so-called unresponsive wakefulness syndrome. That means arousal with no awareness. It's what we used to call vegetative state, or minimally conscious patients. So you have an arousal with minimal or non-consistent, let's say, awareness, okay? So we are talking about really complex patients, sometimes with vital supports, and patients that you cannot move easily around to do tests. Consciousness is assessed, is measured by clinical scales, and this is the golden standard, let's say. You see, it's a questionnaire in which you assess different domains of consciousness. The auditory domain, so you try auditory stimuli, and you see if the patient can follow, in a sense, this kind of stimuli. Visual stimuli, motor function scales, automotor verbal function scale, communication, arousal scale. I mean, it's a test that you have to repeat several times, because you know, also in the duration of the day, the consciousness level may change, so you have to repeat this test. You have to verify if you have behavioral responses, but in the end, there might be more than 40% mistakes, okay? So the accuracy of the consciousness assessment is not that good. Of course, to complement this, the European American guidelines says do something instrumental, okay? What does instrumental means? Do some EEG, do some imaging if you can. Imaging is a problem because vital supports and these kind of things, using an MRI can be a severe burden for this kind of patients. So we should try to get as much as possible from signals. And then one of the things we wanted to test with our patient is to look for the autonomic nervous system, because, you know, heart rate variability, respiratory rate, because these things are modulated from the central nervous system. And so, and you also know, for example, heart rate changes if you are aware about your environment. If something changes in the environment, the way your heart beats changes, okay? So if a disorder of consciousness occurs, probably something may be broken in this process. And so we decided to take a look at heart rate variability, and we started from easy information, so just taking a look at this heart rate variability in patients. We started from EEG and ECG recordings from the clinical practice, so nothing special to be done and to be added to the burden for clinicals and patient. And we observed that actually there is something in heart rate variability. DOC patients have, especially if they are in a vegetative state, they have significant differences with respect to minimal consciousness state in terms of heart rate variability. And if we use this information, in a machine learning model to see if we can discriminate vegetative state from minimal consciousness state, that is a problem actually for these scales. Using EEG only or EEG plus ECG derived information, we could improve the accuracy of our classifiers. So ECG has indeed some information also about this point. So let's come to the main objective of this specific study. We saw that there is something, but we found this paper, this review paper, that says that of course, we can get information on autonomic nervous system, but these visceral inputs are cognitively mediated on multiple time scales. Okay, so we are engineers, we know something about multiple time scales. We decided to move for nonlinear analysis then, and so to add something else, some nice calculations to get some other features on this point. So we started from what? We started from an ongoing study on this kind of patient. It's a prognostic study of patient with severe acquired brain injury. adults, and for those we had more than 20 minutes resting state ECG recording. We are talking about very simple signals from the clinical practice. Okay, so 2 leads and that's it. We had more than 5 CRSR evaluation within 7 consecutive days, so the best we could get for having a ground truth for consciousness assessment, and of course silent consent from patients. Then, starting from ECG, the processing was something very simple, high filtering, that's it, peaks identification, R intervals, and that's it, something really, really straightforward. And of course, we removed artifacts because this patient may have spasms or stuff like that that has to be cleaned in a sense. Then we came to some nonlinear features. Okay, so multiscale entropy, approximate entropy, sample entropy, fuzzy entropy, fractal dimension, why not? And we analyzed those information with a classical statistical analysis to start, okay? The only thing we had to be careful about is that we had to adjust our analysis by age and sex because we know heart rate variability is affected by these quantities. And that's it. These are the results we obtained. As you may see, of course, they're not that Gaussian. I mean, they're not that nice. We are talking about really, really complex and variable patients in the end. But if you compare DOC and not DOC patients, it's evident that all these entropies goes down, okay? And this is something that we were looking for, we were expecting, because we are talking about patient in which the variability, the activity, the complexity of the signal was not modulated by nothing, was actually, for some of them, they were in vegetative state. So we were looking exactly for this information. But this is, you know, what we were looking for because it can be used to improve patient assessment, to say something more about this complex thing to be described. By looking at the analysis results, the differences were significant. Also in a multivariate model, the significances were preserved. And if you take a look at the ROC curve, of course it's not super good, but all of them say something about this problem. And so it's something that we can probably go ahead using. So to conclude, let's say, to discuss our results, we had the opportunity to have many patients' data, even if it's a simple data set, because we just have data from the clinical practice. But we had the opportunity to screen complexity measures of heart rate variability on disorder of consciousness patients. And we had the opportunity to say something just by looking at very simple, low cost and low burden measurements of daily routine. We are going ahead with the large prospective observational studies, so we will go ahead in this direction, and we will try to assess the diagnostic potential, the real diagnostic potential of this thing. The take-home message is that actually you have a lower heart rate variability complexity in patients with disorder of consciousness, and this is coherent with the fact that the responsiveness of the patients to stimuli is reduced. What we want to do now, from now on, is to, for example, try something that is stimulus-induced. So, of course, you know, if you can trigger some heart rate variability in this patient by stimuli, by nociceptive stimuli, by speaking to these people, by try to stimulate a reaction on heart rate, of course, these, the assessment of these quantities can be some way improved, and then of course go deeper, as we were starting to do, in the stratification of minimal consciousness state and unresponsive wakefulness syndrome. Okay, thank you very much.
Thank you very much to all the speakers. I would like to call them back on stage for the question and answer session. So please come. And I also recommend to the other people in the space 35 room to post their questions on the chat so we can see. Please come. So are there any questions from the audience? Yes, there is a question there.
Okay. Palomagno from Pavia. I have a question for Eleanor, I think. My question is linked to about the variability, the interpatient variability, about the PK/PD parameters, and if you consider that, how this variability impact on the final control, and if there is a learning of the individual parameter during the therapy or not.
Thank you for the nice question. Actually, there is variability. There is variability for the 3 drugs, for how the patient reacts to the 3 drugs. We had 24 virtual subjects, and they are all different in the way they react to the drug. So yes, there is variability in that, both in pharmacokinetic, but even in pharmacodynamic. So how the body reacts on the drug and how the drug impacts the body. So that we considered. We saw some differences. Actually, we tried to report there the 50th percentile to give an idea. Of course, it's still a simulator that is limited of what we can do with. It's not, doesn't take into consideration maybe the complex behavior of the human body. But we are going towards that direction. The other part of the question was?
Is the question if during the therapy the parameter of the subject are identified and the variability reduced for that?
Yes, sorry. So we have identified the model on an average subject that was available with 24 patients. And so that we have a model that we used in the MPC, a Kalman filter, that was tuned on the average model, and we used that to perform our predictions inside MPC. Indeed.
Are there any other questions for our speakers? Yes, there.
Thanks. My question is for the first presentation. I found it very interesting. I was just curious about what you mean with the adversarial event, because if I understand correctly, it was like a kind of binary classifier with respect to non-biomedical or biomedical documents. So what do you mean by it? And if you have also thoughts about other third class for unknown document. Thanks.
Okay, it's a binary classifier, but it's not for biomedical and non-biomedical documents. It's for health information technology related and non-health information technology related adverse events reports. An adverse events report is a spontaneous report that physicians and nurses and in practice in medicine, you submit to this kind of database, like the mode of the FDA, when you found there is some problem in using a specific medical device. A problem that can lead to injuries, to death, but it's not quite related to the use of the medical device. It can be, but it's not 100% sure. So these are the adverse events reports that we took into consideration and that we extracted from these spontaneous reporting systems, indeed. Okay.
Thank you. I call also our co-chairs if they have questions. Yes.
Thank you. I have a question for Giulia Sedda. Thanks. We have seen now great advances also in the ability of tracking eye movements also through cameras, even though it is of course not as accurate as eye tracking system. I was wondering what you are foreseeing for your system to be compatible in the future also with this kind of approach, or if you think that this is too far away to come.
Thanks for the question. I think that iLab will be very useful also for this kind of system. It depends on the clinician needs. So if he needs that kind of instrument can be useful for its clinical practice, I think that iLab have to find a way to customize its feature and adapt to this kind of tools.
Thank you.
Thank you.
Daniele Bibbo from Roma 3. I have a question for Andrea Mannini. In effect, you talked about the fact that maybe some trigger can occur in the aspect that you show. Do you think that the patients you examined have in a certain way be triggered by machine or by stimuli that they have in their unconscious status? I mean, they are connected to some machine maybe, so
yes,
it can be already a kind of trigger.
Of course.
And if the database was different, they come from different situation or similar situation, because this maybe can
Thank you for this question. It's a database from approximately 200 patients treated in the hospital, and the signals refers to the admission is EEG assessment that is conducted usually always in the same way. Of course, what we had to do is to just crop away artifact regions and places where we could see from EEG or ECG signals that something was going on, but we had not direct control on other things. So let's say to make things more uniform in this sense, we are considering for the next assessment to do some stimuli patterns that are controlled so that we know the stimulus where it is and we can track it. We were starting from clinical data, so in the end, the only thing that we know is that the assessments are done always in the same way at the admission of the patients, in the same room, in the same conditions, and of course, the patient changes. The patient changes a lot, and there are some patients that are more responsive, some that are really in a really complex condition. So the effect on signals of these things is within the large variability that you could see probably in those box plots, because there are some variabilities that we could not control. Thank you.
Thank you. Other questions? I personally have a question for Enrico Longato. It's actually a double question. So the first one if you had the chance to compare, or even though if you did not present it, with adversarial machine learning techniques for the data augmentation, and if you think that it can be, or if you think that it can be useful, and not based on dynamic Bayesian, of course, networks. And the other is about the application, because it seems to me that the paper and your research is mainly focused on the methodology, which is very interesting. And so I would like to know if the actual application that you presented was from a clinical requirement, a clinical demand, or if it was an application you conceived in the lab because it's challenging.
Okay, so answer to the first question, yes and no. That is, we haven't tried explicitly to run all the possibilities at all levels of the pipeline. At the moment, we focused on just the transfer learning bit, so the final bit of the pipeline, modifying that because it makes more sense in that we have a data augmentation technique that works, and the bit we are uncertain about is how we can combine the simulated data and the real data. The next step will be to go back into the pipeline and restart it using different data augmentation techniques among which obviously adversarial networks, but also just the translations and rotations, whatever they mean, that I was mentioning in the beginning. So it's just work in progress. And as for the second question, that is an interesting point, because this comes, in fact, from a request by the clinicians, because they say, oh, we'll look at the entire history of the patient. Why don't you? Because in general, if you have a few data points, you only have hopes of learning a reduced set of parameters, and then you would use a simple model that just looks, for instance, at the latest visit, whatever it is. But they say no. When we assess a patient, we look at everything. Why doesn't your model? Why should we trust it if it doesn't do what we do? And so that is the application, so the applicative need from which all of this came from.
Okay, thank you. Thank you so much. In the meanwhile, there were other questions coming from you or from my co-chairs here. We have still, I think, a couple of minutes.
Okay. I have one curiosity for Andrea Lusky. Yes. You used the clinical BERT, which is the clinical declination of the BERT. Nowadays, we have other natural language models. Do you expect in the future other declinations in the clinical domain of the natural language models?
I hope so, because if they were, maybe they were even better and we didn't need to fine-tune our models. As far as I know, these are the ShyBERT, BioBERT, and ClinicaBERT are the three only available now. But I hope that in the future, maybe something more related to the clinical engineering and technology aspect of the maintenance of the medical device, more than now they are more related toward the clinical medical aspect and not the medical devices used for clinical duties. Okay.
Okay, I have one curiosity for Eleonora as well. It's partly already answered, but you developed a model who predicts the patient situation, but is the model using the same, let's say, virtual patient, or is a much more simple model?
So basically, the model is done a priori. So the first step is to find a model on the average patient. So we have a patient that behaves in an averaged way with respect to all the 24 we have. And on that, we can try to tune in proper ways what should be like the average response to the drug infusions and all the disturbances we consider. With that said, after we have the behavior, we can use online the model predictive control with that model inside. That is the model part of the model predictive control. And after that, it's going to be just real time, the model predicting based on that what is the proper infusion rate for the real and proper subject we are considering. That is different. And one nice thing is that we just apply the first control action that allows us to somehow mitigate the discrepancies between the model prediction and the actual reality. And by doing that, instant by instant, we minimize that. That's why we can have the luxury to use an average patient, just because we take one step at a time.
I have another question. Okay, you have used as one of the targets bispectral index.
Yes.
Okay. Did you consider, knowing that sometimes bispectral index can have different sensitivity and specificity owing to age and specific pathology, did you consider to use in the future some other indexes and maybe introduce some other variables as the age-specific pathology and so on?
That's a very nice question. Actually, in our models, the age is taken into consideration. So one of the parameters is the age, the gender, and many others. So regarding the pathologies, the next step is to consider, for example, the pathologies related to the heart, and this taking into consideration the hemodynamics, since we have problems in anesthesia, especially with the subjects that have problems on the heart, whatever pathologies can it be. So that is going to be a next step, taking into consideration at least a little part of that. And with regard to other indices, of course, there are at least a couple that are used as the standard practice in Canada and the US. We are using the European one. That's the main reason. But actually, yes, we could even switch and take into consideration those, but just for the moment.
Thank you. Other questions for our speakers of this first track?
I have a question for Enrico Longato. It's for sure an interesting direction because it's an interesting way to bridge the gap between methods, advanced methods, theory, and what happens in reality. So data usually are not available in the amount that are really needed from a theoretical background. So I was wondering if you have already explored if there is a saturation, a limit in the simulated data. I mean, is there any limit beyond that beyond that it is not useful to go on with simulation for training your model?
I get what you mean. So yes and no. That is, we haven't done a systematic analysis of that yet, because as you might imagine, I haven't shown it in the slides, but there's a whole hyperparameter optimization bit that requires multiple iterations, and so you would need to train a different network every time you iterate, and so the computational cost of this would be exponential, and it was not in line with the time we had for this, but this is the next step we're going to be exploring, and we're going to do that using larger databases, because you've seen in my presentation that was rather a small one, even though it covered a decent chunk of Italy. We are going to have a couple more databases, one from Italy and one from Portugal, where we have bigger numbers, and so we can study whether the point is how many simulations you do, how many patients you insert into the simulations, and how these work with each other. And then, and this is something we already started exploring, is what happens if you have few data points but multiple data sets, because transfer learning works not only from simulated to real data, but in general from two tasks that are different. And so we tried that, and it actually does work. Again, the question is the same we posed, that is, what is the critical mass of data that you need? And for that, we will have hopefully an answer by the end of the year.
Thank you. We have time for another very quick question. If not, I have a very...
I have a naive curiosity for Eleonora, actually. So, how far are we from the clinical practice of this model?
That's a nice curiosity, actually. So, it depends of the research group, mainly. So, we have, even in Italy, universities that tightly interact with clinical practice. It is not easy, since you need to have the support of an anesthesiologist team, because it's not like we can act in a retrospective way and use the data they send us. No, we need to be there, and it's risky. It's not easy. It's a big task, and automating the loop, like closing the loop of control, it is big. It's still something big that scares, but we have, and we are not the US, in which it's very easy to start clinical trials, to start this kind of collaboration. So even in Italy, we have, for example, the University of Brescia that has a very strong collaboration years now with the clinical practice. We are starting taking the interest in this kind of work. But once, even though we have teams that work with anesthesiologists, it's long. It's long, it's not easy, it's a complicated control problem, even though now I just showed you some little hints of how it could be complicated. There is some work to do in that direction. Thank you.
Thanks.
Okay, so I think we are running out of time, so I would like to thank again all our speakers and all the colleagues sharing with me this session. I hope it was interesting for you. And of course, you will have the chance to meet our speakers during the conference. So if you have further questions or you want to discuss about the research, it's a great opportunity to meet during this conference. So thank you very much.